All right. If you remember from last video, I am Ruchi. Right again. And now I'm equipped with better markers. I mean better erasers. So that's a great thing. Today we're going to talk about networks, neural networks. Previously we were talking about networks like networking technology, like servers and such. Now we're talking about neural networks. Okay, let's start with what a neural network is. Okay, neural network is nothing but a function. Okay, it takes. We can call this our neural network. We can call this our neural network. That function f. It takes x. Oh, it looks like there's a glare. Let me just turn this like thing off. Hold on. Hopefully that's better. And this too. Okay, cool. So this neural network neural networks are nothing but functions. Okay, it's a function. It takes an input x, and it produces an output y. That's all a function does, right? It does random stuff to an input. It's like a black box, and output some other number, right? Now this function though, this neural network function, has an interesting property in that it can actually edit itself sometimes. This is what it does normally. It takes an input and it produces an output, right? But let's call a different version of this function in training mode. You put this function in training mode, and it gets the ability to edit itself. Interesting, right? This is what happens. Okay, in order for the function to edit itself in training mode, it needs another input, an extra input, and this input is actually a special one. It's the expected output. Okay, what the function does is it takes the regular input and it takes the expected output of what I want to be the output. This expected output is what I want to be the output for this input. Okay, and then the function creates y. Again, it creates the regular output based on this. It doesn't use this yet. Okay, and the second step it does is it takes this guy, it takes the expected output, what I want to be the output when I put the input x, and it takes the actual output y, and it compares the two, and it produces, it compares the two, and it computes the loss. Computes basically how different the actual output is from what I want the output to be. And let's call that number L, loss. And then it uses that number. It uses this number L, and it uses that number to edit the function productively. So what this ends up being is that the function is edited such that the loss is minimized. We want to we edit it so that in the future, like I edit it such that next time I run it with this exact expected output, and this exact input, I get a y that's closer to x prime. So in that way, the function is edited productively so that it becomes more and more. It becomes a function that produces what I want more often from given inputs. Okay, so that's what a neural network is. But normally, right? That's just in training mode. Normally, it just does this. That's it. Normally, it just does f of x equals y. So neural network is nothing but a function. Fancy function. A lot of hype behind neural networks these days. Special cleaning liquid. Now this thing can go really quick. But yeah, so like basically it's just a function. Nothing special to it. People think neural networks, a lot of hype, loss functions, all kinds of crazy words people are using. Not that important. Okay. Now, so that's great, right? You have expected outputs. What happens? I'm going to talk about a different kind of neural network. I'm going to talk about an autoencoder. Okay, this is one of my favorite types of neural. I just learned about it recently, so recency bias as well. But autoencoders, right? I'm just gonna abbreviate E. Wow, this thing is the liquid is too strong. A. Oh man, it's like way too strong. Oh my god, maybe this thing is dead or something. Okay. Oh yeah, maybe. Anyways, autoencoders, right? Here's the point of an autoencoder. Um, remember how the neural network that I just talked about, it took an expected output and it computed like the loss between the expected output, the difference. It computed how different the expected output was from the actual output. Use that loss to go into the function, edit the function so that the next time the function would run, it can minimize that loss or make that loss smaller. But that required me to have an expected output, right? That's called supervised, or that's labeled training data. I'm pretty sure that's called supervised learning. The neural network is supervised. I'm giving it like what I want it to be. Like I'm giving it labeled data. I'm giving it expected outputs. But sometimes there's types of neural networks that don't need that. So okay, how do you have a neural network that how is it going to get better? How does it get better if there's no labeled if I don't give it an idea of what I want it to be? Okay, well that's the special thing about autoencoders. Autoencoders are unsupervised, do unsupervised learning. They don't need any labeled data. Okay, this is how it works. All right, I take data X. All right, here's my input. It's still a function, mind you, it's still a function. But what's interesting is basically here's what's special about autoencoders. Okay, autoencoders are two parts. All right, basically one part is an encoder, one part is a decoder. All right, the encoder's job is to compress data. Okay, so I get X. The encoder takes X, right, and it turns X into X prime. What's it's a so each one of these is a function. Okay, this is a function, and this is a function. Okay, and the autoencoder is these two functions. Basically, it's another function. Okay, h of x maybe we'll call it. It's all functions. Now, the encoder takes X and turns into X prime. Okay, and what the most important thing to know about this, what an encoder does, is that it makes it smaller. Okay, it makes X smaller. X prime is smaller than X. Okay, and usually it's smaller in terms of dimensions. So like I have like maybe a huge like 100 dimension vector. What is a vector? It's just a list of numbers. Okay, 100 dimension vector it means I have a vector that's 100 numbers. It means I have a list of 100 numbers. Okay, this X prime might be 40 numbers. It's a list of 40 numbers. So this X might be a list of 100 vectors. The encoder turns it into a list of 40 vectors, of 40 numbers. Holy shit. So basically it makes it smaller dimensionality wise, and maybe otherwise as well. Maybe there's other ways to make things smaller. Probably there is. Definitely there is. It encodes it. It encodes it into a compressed form of itself. Now, remember I talked about there's no labeled data. It's right. There's no labeled data. In fact, what it uses is so. And then no, what happens next, right, is the encoder turns X into X prime, and the decoder, okay, this is f of X into X prime, and the decoder takes G of X prime and produces Y. Okay, so you might look at this like, what the hell is going on? All right, I put X into H, and I get Y. All right, that's my autoencoder function. But really what I'm doing is I'm encoding X into X prime and then decoding X prime into Y. That's so dumb. Like, but is it? Right? Now let's look at what happens, all right? Basically, what happens next is X is compared with Y. And remember that loss? We compute loss. We compute the loss, we compute the difference between X, the original input, and Y, the decoded, encoded version of the input. It's different. Y is not X. Y is the decoded, encoded version of X. Compute the loss, right? There might be a loss. Maybe I encoded the input data and I got some number. I got some other piece of data, and then I decoded it, and what resulted is like something close to the input data, but not exactly, because I encoded it and then I decoded it. There's a bunch of extra steps where I did stuff to the data, and it's not exactly like the original data. And I compute the loss, and then I use this loss, right, to edit the decoder function and the encoder function. Basically, I use it to edit the autoencoder function. Okay, and so that and what do? I use the loss in such a way to edit the function such that I edit it productively. I edit it such that the loss will be minimized next time. Okay, and what this means is this function, the autoencoder, what it's doing is it's learning to minimize the difference between the input data and the reconstructed version of the input data. Okay, and there are a lot of interesting things that come from this, right? One is dimensionality reduction. Remember, I said that it turns into a hundred. So what's interesting is, remember, no label data. Okay, we're not using any label data. We're using unlabeled data. We're using the input data itself to train the thing. It just takes the input data and it learns how to be itself, how to be the best version of itself, how to make sure the difference between the reconstructed data and the original data is minimized with just the input data. There's no label data. There's no expected output. Okay, so yeah, isn't that awesome? Definitely. But what is it useful for, right? Neural networks, it's pretty much immediately useful. Immediately obvious what they can be useful for. Autoencoders, not so much. Autoencoders, not so much. What can it be useful for? What can it be useful for? Or so remember I said that the input data could be 100 dimension, like a dimension of a dimension of 100, the input data, and then it could be encoded into something with a dimension of 40, right? And then reconstructed back into something with a dimension of 100, right? Now, if the autoencoder gets really good, right, the difference between the reconstructed data and the input data is so small that essentially it's learned how to encode input data into a much smaller dimension and then reconstruct it back into 100, back into the original dimension, with like very small difference between the input data and the reconstructed version of the data, which means it's learned a really good compression algorithm, albeit a lossy compression algorithm. Okay, so lossy meaning it's not perfect. Okay, it's not 100% perfect between between X and Y, the input data and the reconstructed version of the input data. Remember, this becomes X prime decoded, and then it gets encoded into Y. So basically, I know how to drop my autoencoder can drop from 100 dimension to 40, and this is a decent version of the data. Like I can reconstruct it back into something very similar to the 100 dimension type of the data. So what's great, what we're looking at here is dimensionality reduction. Dimensionality reduction. Like if I have a really gnarly, if I have some kind of really gnarly data with 100 dimensions, that is actually pretty gnarly, right? Um, and I want to do some crazy ML on it, right? Maybe that's a big amount. That's a lot of data. I need a lot of compute for that, right? How do I make that cheaper? I don't have infinite money, right? So what I do is I use an autoencoder, which learns a compression algorithm, and maybe I don't need to be perfect. It can be lossy. The autoencoder learns a compression algorithm, which becomes really effective at reconstructing a compressed version of compressing and decompressing this data, and so I can reduce the dimensions to 40, and then run my ML on that type of data, and this will be way cheaper, and maybe I'll get the same benefit, and probably get the same benefit with very little loss, and so dimensionality reduction. Now, here's for a pretty crazy version of what this autoencoder can do. Here's some crazy shit. About to tell you some crazy shit right now. Some crazy fucking shit. Okay. So this autoencoder, right? What else can it do, right? It learns how to reconstruct um, the input data to where the input data and the reconstructed data are not that different, right? Um, what can that be useful for as well? Well, besides dimensionality reduction, it's really good at anomaly detection. Basically, if I feed my autoencoder normal data, say X, this represents normal data. If I feed X to my autoencoder, it learns how to produce Y. Right? Y and X are basically similar, right? Maybe I could say like X is like basically Y, right? Now, if I keep feeding shitloads of the same kind of X to Y, then my autoencoder is gonna get really good at to this. So assume that X is like normal data, right? And X is like kind of all similar, right? If like I'm feeding like I'm feeding like X1, I'm feeding 100 different types of X. So X1, X2, all the way to like X100, or maybe X like 1,000, or maybe X 10,000, right? A shitload of X, and they're all kind of the same, right? Now, the autoencoder learns how to reconstruct X. That's one thing about autoencoders, right? It's learning a compression algorithm, but for a specific niche type of data, right? So it's a niche compression algorithm for a specific type of data. Now imagine, okay, in all these X's, right? Now I'm not training the autoencoder anymore. So that was kind of the loss function where it's editing itself. That's a training mode of the function. Imagine I'm not training it anymore. Now I'm just using an autoencoder like to perform inference, where I'm just getting the output. I'm just doing H of X and what is Y. I'm not comparing Y with X, making a loss and changing H up anymore. I'm just doing inference. Um, Imagine in all these, I trained it on all these X's, computed the loss with all these X's, use it to change the function, and now I'm throwing a Z in there. It's like an anomaly. It's a different type of data. It's not normal. It's not what the autoencoder is really good at compressing X's and reconstructing X's, and having the difference be very small. Now, the difference between Z and it creates Z. It encodes into Z prime and decodes into Y. And now you can see that Y and Z will probably be very different. Z will not be that close to Y, because the autoencoder, meaning this part and this part, the encoder and decoder part, which is the part of the autoencoder, encoder, they know how to compress and decompress X's. The algorithm did not learn how to compress and uncompress Z's. So it's an anomaly, and the loss is so big that you can flag it. So basically, the autoencoder has learned what normal data looks like. It's extracted features of what a specific type of niche data is like, and so it can detect anomalies. So in like networking, right, like the server video of last video, um, it can detect that there's like an anomaly. There's like maybe about network traffic, a bunch of different packets. It learns. You give it a bunch of the same kind of data. Give it like what normal data is. It's going to extract what normal data is. Going to learn what normal data is, and it can flag anomalies because the loss is going to be huge between the anomaly and because between the anomaly. This is going to be so the loss is going to be huge. It's not like the original version of the anomaly and the like the encoded decoded version of the anomaly is going to be so different. You're going to be like, holy shit, this is like a lot of like, what the absolute fuck am I seeing, right? So that's how that works. Nice. Let's just go really quick about like recurrent neural networks as well. Let's talk about that. Recurrent neural networks, RNNs, are I told you about neural networks, right? They take recurrent neural networks deal with like data that's in a sequence. So like RNNs, deal with data that's in a sequence, right? So like imagine some data is in a sequence, right? Like I can't just like predict. So like think about this, right? I and then I predict the next word in the sequence. I am. I predict the next word in the sequence. I am feeling, right? So if I'm gonna predict the next word in the sequence, right? I can only look at the previous word. If I'm looking at I, maybe I can predict am. But if I'm looking at am, maybe I could say hungry. But the real word was feeling. You see what I'm saying? Basically, I need the context. I need the context. Or if I just look at am, I'm gonna be like confused as hell, right? I need the context. Okay, if I look at feeling, I'm gonna be confused. Maybe feeling, I'm gonna say like I don't know, felt or something. But you know, the in context is different, right? Basically, okay, the point of RNNs is it's another function. Okay, I'm producing a y, right? I get x1, y. I produce a y1, right? I'm also gonna keep creating h1 based on x1. It's gonna be a compressed version of h1, and then the next iteration I'm gonna take f x2, right? I'm gonna take x2, and I'm gonna take h1, which is like my compressed version of x1, and I'm gonna produce y2, and then and that's that's what this is maybe, and then I'm gonna do the same thing, and then maybe like later on I'm gonna get like f x like 100 h 99. I can produce y 100. So I can get like all the context. I get all the context. This whole sentence, I'm predicting based on this sentence. The next word based on the entire sentence, and not just this one word. Because some things like sentences, they have context, right? I need in sequence. The word is different in sequence. So that's the entire principle of RNNs. And there's actually something called LSTMs too. Basically, as RNNs get super big, there's like a vanishing gradient problem. I don't totally understand it, but it stops like remembering like things like way earlier. Like if I get to 100, it stops remembering number one. Basically, something about how this H1 gets compressed. This is the hidden memory, hidden state. So they created something called LSTMs, which are pretty complicated. I don't really understand it. They've got like memory cells and gates, and basically it's just some way to like it's long short-term memory networks, LSTM ends, I guess, and yeah, they hold memory for like longer sequences, and I don't totally understand it. And then after that, right, they made Transformers, not the movie, not the robots. Transformers. These guys, there's a paper that came out called "Attention's All You Need," and that's what they did is something this principle called self-attention. I don't totally understand it, but yeah, like pays attention to different words. So instead of like sequential processing, it's like parallel processing. It's like more efficient when you use like GPUs, and like yeah, they looks at all the words in everything in a sequence, like before and after it, and it predicts the thing inside. Kind of interesting. Yeah, nice, cool. As you can tell, I don't really understand too much about transformers or LSTMs, but RNNs I kind of get, and then autoencoders I get a little more, and then neural networks I kind of get pretty much. But yeah, okay. Thank you.